Okay, so we consider a two-dimensional wave equation. Okay, this wave equation describes the vertical displacement of a point x, y in a circular membrane. So we just set the circular membrane to be the x, and actually it's just a circular disk in the plane, and for all t greater than or equal to 0. So this is the, okay, and so because that the region is circular, as we mentioned last week, we will have boundary conditions on the boundary of the circular membrane. And you know, the boundary of a circular membrane is just a circle. Okay? It's a circle. So, so this is like the rectangular membrane we discussed in last section. Okay, last section. So, all right, and with so we will fasten the boundary. Okay, so the boundary actually is all right. So we will fasten the boundary of the circular membrane. Okay, that means that we will set the boundary condition to be 0. All right, around the boundary of the circular membrane. Okay, so the boundary is in a particular shape right now. Okay, and so we will transform the wave equation into a form in the polar coordinate. And we will set r equal to r cosine theta, y is equal to r sine theta. Okay, so that the coordinate transformation is okay. For all x1 minus the origin is O. Okay. And so R is equal to theta as I said it. Okay. So this is called we call V U. We call U. and r theta is in going to be, so maybe I will say pi. Okay. Okay, now relate u tilde r theta t to be u x r theta y r theta and t, and then u x y t becomes to u tilde r x y theta x y and the t. Okay, so we have that, and we did a lot of colonial transformation in section 12.4. So now so you know this is comes to tangent theta is equal to x. Okay. So by chain rule, right? We have u x equal to u tilde r x plus u tilde theta theta x. Okay, this is the partial. The first partial derivative of u with respect to x. All right, can be written this one. Okay, because that u. Okay, u expressed as u tilde composite with that of everything here. So and uxx. Okay. The second order partial derivative. So we can do a lot of x plus u theta x. Okay, so we will do the partial derivatives, and there's some algebraic manipulation. So at last, you will have or x plus to u tilde r theta r x theta x plus square. Okay, this is square, and u tilde theta theta x square plus So this is corresponding to second order partial derivative of u tilde with respect to r and theta. And this is corresponding to first order partial derivative of u tilde with respect to r and theta. Okay, so that is the case. Right. All right. Now, know that. So we will need the partial derivative of r with respect to x, the partial derivative of theta with respect to x, other things. So so we know the x. Okay, x here. So as a function of x and y. So when we take the partial derivatives, we find this is x divided by square root of x squared, and so this is x. So the okay. So this is corresponding to x is equal to r and rx. Okay. And for theta, because theta and x is arctangent, so we have 1 plus y x squared. So this is the derivative of arctangent, okay? And relative to this one, so this is minus 1 x squared. If you forget what is the derivative of arctangent, well, you can do it from say here. Okay. Because y and x are independent variable, right? So when we take, okay, because y is r sine theta, right? Y is r sine theta. R is a function of x and y. Theta is also a function of theta and x and y. Okay? So when we take, this is equal to 0, it's y. Because y is y, right? Y is independent variable. So the partial derivative is 0. But because y is here, so the partial derivative maybe I use another color. Okay, so this is r theta, sine theta, plus r, and cosine theta, and the theta x. Okay, and this is equal to 0, so this implies that theta x is equal to minus x. I'm sorry. X. I'm sorry. This is Rx. Okay. So this is Rx divided by x sine theta, and this is r cosine theta. Okay, and so, and we know Rx is equal to x divided by r, right? So we have x divided by r squared, and this is tangent theta. But tangent theta is equal to 1 divided by x, so this is become to minus 1 and the r squared. Okay, so immediately you can find the partial derivative of theta with respect to x is 1 minus. And we can compute the same thing. For here, after some manipulation, so you have minus y And here you have x squared plus y squared minus r squared y. Okay, so you get the same result. Okay. Alright, so you have both derivatives here. Okay, and the Rxx is equal to, so here you take the particle with respect to x again, so you get r minus x rx divided by r squared. Okay, and this is 1 over r. Okay, and minus x x and the r cubic, right? Because this term is 1 over r, okay, and this term is minus x times r x r squared, but I multiply r in the numerator and the denominator again, so I get r cubic. And the reason why I want to use one is r times rx is equal to x, so I get x squared. Okay, and so so I have r squared minus x squared, so this is 1 squared and r cubic. Alright, how about theta xx? Alright, and theta xx is this one, so theta xx is minus 1, and this is minus 2 cubic and rx. Okay, alright, and once again rx is x divided by r, so this becomes 2xy, and this is r post power. So now, well, we have everything, right? We have that. Okay. So now we substitute everything to here. So we have uxx, which is equal to x squared r squared u cubed r minus 2xy r cubic u cubed theta plus y squared whole power theta. Okay, and plus y squared divided by r cubic u r theta plus 2xy whole power and u theta cubed. So this is the manipulation. Now, similarly, so we can go over the process for u1. Okay, when we go over the process, we find that we have y squared r squared u cubed r plus 2xy cubic u cubed theta plus x squared whole power u theta cubed plus x squared y cubic r cubic, sorry, u r cubed minus 2xy whole power u theta. Okay. So now alright, so the processing, you add up them together and you find that the coefficient for u or r is just equal to 1 when you sum up these two coefficients together. Right? And the second thing is that we cancel the mixed second order partial derivative here. We cancel them. And we have for UR tilde, when you sum up together, we have 1 over R. And U tilde R. And we cancel this part. So finally, for here we have 1 over R squared. And U tilde, say. Okay, so this is our, so which is the Laplacian in polar coordinate. Alright, so the two-dimensional wave equation, okay, in polar coordinate becomes 2 equal to C squared okay, for all R theta in the x minus the origin, okay, for all t equal to 0. With a boundary condition. Okay, the boundary condition is U tilde theta t equal to 0 for all theta in the boundary of x. Okay. Okay. And the two initial conditions. U tilde theta 0 is equal to FR theta for all R theta in x. Okay. And U tilde, the initial velocity, this is the initial displacement, this is the initial velocity. Theta. Okay. So the initial condition is good for all points in the circular disk, including the origin, the center of the disk. Okay. Even though the differential equation, the partial differential equation, is only good for the circular disk without the center. Why? Because at center, R is 0, this is infinite. Okay, so we have to exclude the center. But for the initial conditions, okay, we will find solutions such that the displacement and the velocity at the origin, at the center of the circular membrane, should have some value. Okay, so we have the initial conditions and we have boundary conditions along the boundary of the circular disk. Alright, now in the rest of this section, we will consider a kind of special case. Suppose that when the initial displacement f theta, and the initial velocity gr theta are radially symmetric, i.e. Fr theta is equal to Fr, and the gr theta is equal to r. Suppose that we have radially symmetric initial displacement. So the initial displacement, okay, just depends on the distance, the point, the distance of the point from the origin. Okay, so we have I think I should say that circular symmetric, not radial symmetric. Okay, circularly symmetric. Okay, so that is independent of theta. Okay, it's independent of theta. So we will determine solutions of the boundary value problem. Okay. Of the form, or I just say the solution of the boundary value problem is also circularly symmetric. i.e. the u r theta t becomes the u r t. Okay? Thus, we will have u tilde equal to 0. Okay? So because the solution is independent of theta, and so this term is 0. This term is 0. And our boundary value problem becomes to move on. Okay, and for r from 0 to r and t is 0. So this is our 12.10.1 with a boundary condition u tilde t equals 0. Okay, so when r equal to 0, when the radius is equal to when r is equal to radius of the circular membrane, capital R, is 0 because we fasten the membrane along the boundary. So the displacement of the membrane along the boundaries is 0 for all time. Okay? So this is the 12.10.2. Okay. And two initial conditions. U tilde 0 is equal to FR for all 0 from R from capital R. And the U tilde T R 0 is equal to GR for all 3. Okay, so R includes 0 into the center of the circular membrane. Okay, so we have, and actually, you will see that, well, you know, the little r has another end point, 0, right? So we should have another boundary condition implicitly. What is that implicit boundary condition? Well, we should have additional boundary condition. So this is a boundary condition at r equal to r, right? Now an additional boundary condition at r equal to 0. What is that? What is that? Well, U tilde 0t is finite. Okay, for all t, right? We should have a bounded solution, right? It's 0 because this is physically meaningful, right? Physically meaningful. So we should have an additional. Actually, this is implicit. It's not explicit like this one. It's implicit. Okay, so we have that. So we have to be aware of this additional boundary condition. Okay. All right. So now we are solve the PD here, and this PD is a little bit different from the wave equation, right? In the rectangular coordinate, is that we have the first order partial term. Oh, all right. So we have the first order part. This is here. It's not 2. Okay, and so we will use the method again. The method of separating variables to solve this PDE. Okay, so step 1. Step 1, we will have 2 ODE from the wave equation. Okay, in 12.10.1 here. So we let U tilde RT equal to WR and GT. Right? So it's separate variables. And so when we put to the equation here, we will find that the W, G of that means the second derivative of G with respect to T equal to C squared, and the G and the W from plus 1 over R from. Okay, so this is our so this one, and so this is implies that G double dot divided by C squared G is equal to 1 over W, and the W From plus 1 over r of from. Okay? Alright, and this is we write this is to be minus mu. Okay? So we said this is minus mu. Okay? And that is a constant. I just put minus for convenience. Okay, so it's a constant. Okay? And so we have two ODEs. Implies that W from plus 1 over R plus A plus mu. Okay, equal to 0. So this is called 12.10.5. Okay. And G is that plus mu C square G equal to 0. 6. Okay, so we have two ODEs. Okay. But this, what is that? This is a quite familiar differential equation. It is the basal function equation. How can we say that? Well, when we multiply with r, okay, so this is actually equal to r. So let me write it into okay. So what is that? The basal equation of order mu equal to 0. Okay, so it's 4. Right? And the mu is our eigenfunction. So this is the Sturm-Liouville problem, right? We encountered before. Right? The Sturm-Liouville problem with mu is order equal to 0, but we have the mu here. The mu here is just a lambda, right? We discussed in chapter 11. Okay? So we learned that. And we have some experience about this. Okay, so we have some experience about that. And for that, so for the second step, we will solve these two ODEs. So now, right, with boundary conditions. Right, so we have. So what is the boundary condition? Right, so the condition. The boundary condition we have is here. We have one explicit boundary condition and one implicit boundary condition. The explicit says that 0 is equal to and this is equal to WR gt, okay, for all t. Right? This is the explicit boundary condition. And this explicit boundary condition implies that the WR should be 0. Okay? That should be 0. So this is the 12.10.7. Implicit boundary condition is that U tilde C of t W 0 Gt, okay, is finite for all t. Okay, so it implies that W0 is finite. Okay, so this is the implicit boundary condition. Right? So actually we have two boundary conditions. One is explicit, the other is implicit. Okay? So this is the explicit boundary condition at r equal to r. Explicit at r equal to 0. Okay, so now we have a Sturm-Liouville problem. Okay, we have Sturm-Liouville problem now, which is R plus okay, so we have Sturm-Liouville problem, and okay, so with two boundary conditions in okay, but we have experience. So as discussed in section 11.5, okay, a general solution we can have bounded mu, right, is equal to k square positive we can only have mu, the eigenvalue to be positive, such that W 0 is finite. Okay? And I can, alright, what is that? Oh, so I want to set something, but well, I can, I give a full exposure to this process. Alright, okay. As discussed, it will cost some more time. Okay, a general solution of this one, general solution, this one, because it's a second order ODE, right, and linear, so you will have two independent solutions. All right, so W R is equal to C1 J0 R mu plus C2 Y0 R mu, where J0 R mu is expressed by a power series minus mu, k, 2 to k, k factorial, x to k. Right? So this is J0. And what is Y0? Y0 is 2 divided by pi J0 R mu times initial log divided by 2 plus gamma. Okay, so this is gamma. Right? It is not R, it's gamma. Okay. This is all your constant. I will explain again. Minus mu, k minus 1, hk, we use k and 2 to the 2k's power, k factorial, x, 2k. Now I will define what is h. H0 is defined to be 1, and the hm is the partial sum of the harmonic series. Alright, it's 1 over I, sum over from I from 1 to m. Okay, and all your constant gamma is defined to be the limit as m goes to infinity of the hm minus the logarithm of m. Okay, so this is what we had in section 11.5, okay, when we discussed the Sturm-Liouville problem. Okay, so we have, and so this is corresponding to, okay, it's not the Bessel function of the first kind of order 0, it's just corresponding to that. Because we have a parameter mu here. And this is corresponding to the Bessel function of the second kind, okay, of order 0. So this is what we had. And now, so for every not mu here, we have any eigenvalue mu here, we have solution. But as we discussed there, and then note that y0 r mu, okay, is unbounded. Okay, near the endpoint r equals to 0. Why? You know, we know this one by root test. We know the J0 always converge. Okay? So this is final. But here, when r is 0, logarithm is minus infinity. So it's explode, right? Because of this term here. So that's why y0 is unbounded near the endpoint. So this implies that the C2 is 0. Okay? If C2 is not 0, this is unbounded, right? This explosion, when r equals to 0. So, and we require by the implicit boundary condition. Okay? So we have the implicit boundary condition because that at r equals 0, we should have a bounded solution. Okay? So this implies C is 0. The second thing is that when mu is less than or equal to 0, then J0 r mu will be greater than 0, always 0. Look at here. When mu is non-negative, 0 when mu is 0, of course this is constant, is equal to 1. I think it's 1, okay? It's not 0. But when mu is negative, minus mu is positive. So everything is positive, right? Okay? So this is greater than 0 for all r greater than 0. Okay? Which violate the explicit boundary condition. Equal to 0. This is impossible, right? Because we require the solution when little r is equal to capital R. This should be 0, but J0 never 0, never. When mu is non-negative. Okay? So consider the only possibility is that mu is equal to k squared and 0. Okay? And the boundary, the explicit boundary condition at r equal to r requires what? Should be 0. Okay? Implies and C1 cannot be 0 because if C1 is 0, then W is 0. It's trivial solution, right? We don't want any trivial solution. So this implies that J0 R K squared is 0. It's 0. And what is that? Well, so this is equal to, what is that? This is equal to J0 KR is equal to 0. Okay? What is J0? J0R is equal to summation k from 0 to infinity minus 1k choose equal k factorial k factorial. This is x to k. Okay, so this is the Basel function of the first kind, okay, of order 0. Okay, so you compare this one. When mu is k squared, you can move k squared k to here, combine here, and you leave minus 1 here. So you get that. Right? So this just implies that this should be the case. Okay? Right? So from this is the knowledge we get, right? We get from the discussion of Sturm-Liouville problem. So we know immediately that the mu can only be positive. And so we set mu to be equal to k squared. Okay, k squared. So that this constraint comes to this constraint. And we know the Bessel function of the first kind of order 0 it's something like that. It has a lot of zeros, okay? And this is symmetric. Okay, and this is 1 here, and we call this is alpha 1, alpha 2, alpha 3, alpha 4. Okay, so we have this is positive roots of this Bessel function. Okay. Right, so we let alpha 1, alpha 2, etc. be the positive zeros of J0x. Then we have K M R equal to R for M for M. Okay, so KR, actually K should be. So the solution, so when K equal to Km, and Km is defined to be alpha m divided by R, okay? We have non-trivial solution of 10.9. Satisfying the explicit boundary condition at R equal to R, and the implicit boundary condition at R equal to 3. Okay, so we find solutions satisfying the two boundary conditions. Okay, so this is our solutions. And we know we have non-trivial only if K is equal to Km, if it's equal to this number. Okay, so with this number, we go back to solve the second now. With mu equal to Km squared, okay, which is equal to alpha m over R squared. A general solution, okay, a general solution of the ODE in 12.10.6. Okay. G GM T equal to AM cosine lambda MT plus BM lambda MT. What is that? I maybe it is the G dot plus mu is here, so plus Km C square G equal to 0. Okay, so we define the eigenvalue to be Km C, so this is C alpha M over R. Okay, so that is it. So this is the general solution we have here. So hence, HM delta RT, which is equal to delta NR GMT, and so this is AM cosine lambda MT plus BM. Oh, forgot sine, forgot to put sine together. Is 0 Km R solutions of our boundary value problem. Right? In 12.10.1, okay, and 10.2, which are called eigen functions. Okay, of the boundary value problem, okay, corresponding to eigenvalue lambda m, which is equal to Km C, so C alpha m to the power for all m, for all natural number m. Okay, so this is the second step. So we solve two ODEs to get eigen functions of the boundary value problem. Okay, like that. Okay, and so after the break, we will solve the original problem with initial conditions together. Okay, with initial conditions together. Right. So this take a short break for 5 minutes.